Hey Beaklings, it's Mr. Boylan. I wanted to talk to you about some things that we covered in class, energy and talking about reactions, things like that, ATP, metabolism. Okay, so here we go. Let's get started. So, energy is the capacity to perform work, right? Work is performed when an object is moved against an opposing force, for example, friction, gravity, right? Kinetic energy then is the energy of motion. And moving objects work by transferring motion to other matter. For example, the bicycle is contracting muscles, and that's pushing down the pedals, propels the bicycle, right, turning the tires on the street. It's something as simple as rubbing your hand on a desk, right? You can feel you're using that kinetic energy, and the desk is probably getting hotter underneath. Okay, heat and light are both examples of kinetic energy, and that's going to be very important as we go through. If you think about it, the heat that is produced by a lot of reactions, that's just, if you remember your vocab, that's just random molecular motion, right? So heat is definitely kinetic. And light, oh boy, that's going to be a big part of photosynthesis. Light is really just electromagnetic energy. It's just waves all around. So of course that's kinetic as well. Okay. All right, so then potential energy, this is the energy that's stored due to location or structure. So as you can see here, there's a mountain biker at the top of the hill here. He has a lot of potential up here, okay? Whereas if he was at the bottom of the hill, he would have less potential energy. In Bio 1 Honors, we don't talk too much about the location. We care more about the structure. Just like with kinetic energy, it's the energy of motion. We're not really talking about like muscle movement as too much in Bio 1 Honors. We're talking more about random molecules moving around, things like that. So in Bio 1 Honors, when we're talking about potential energy, we're usually talking about chemical energy. And what that is, it's the energy of the bonds inside of these molecules. Remember, we talked about how macromolecules and stuff, how they have all this energy, carbs especially, right? And lipids store a lot too. We can rip apart carbs, be those carbon-hydrogen bonds, pretty easily. We have a lot of enzymes to do that. Okay, so there's a lot of potential there to do some good. And that's the potential energy that we're talking about here. Now, again, it could be the location, okay, but generally we're talking about the structure. All right. And of course, you can convert these, right? You can turn the potential energy into kinetic energy just as a cyclist did. So he was at the top of the hill and boom, there he goes, right? So how can an object at rest have energy? Okay, well, like we just said, its location or its structure. Okay. So, moving right along, we now are talking about the two laws that govern energy transformation. So we're talking thermodynamics here, okay? And thermodynamics is a study of these transformations that occur in a collection of matter. Any science class really does this, but as biologists, we want to use the word system to represent the matter we're studying. Surroundings is anything in the universe outside our system, and it can affect our system, right? So, the laws of thermodynamics. Okay, here we go. The first law is called the law of energy conservation, okay? And it's kind of goofy to think about. This really means that the energy in the universe is constant, right? You can transform it, you can transfer it, but you never create it and you can't get rid of it. Energy is always constant, and that's kind of weird to think about, right? So the thing is, what happens then as we transform or transfer it? It does kind of change forms, right? And that brings us to our second law. Before we talk about our second law, there's this vocabulary word you should know, entropy. I like to think of chaos when I hear entropy. Entropy is the amount of disorder in a system, okay? So if something was very structured and organized, okay, and then all of a sudden became disorganized, that's entropy, okay? One of my buddies talks about it. He has a beaker, and he'll hold the beaker up in front of the kids. I don't know if he actually does this. And he'll drop the beaker on the table, and psh, and he says, oh, there you go. There's entropy. There's chaos, right? You had this beautiful beaker, and when it smashes, now the thing is, can you ever make that beaker again? Maybe, but that's going to require you to do a lot of work. That's what the second law is all about, okay? The second law of thermodynamics simply says energy conservation reduces order in the universe and increases its entropy. What that means is no matter what work you're doing, you are actually increasing entropy in the universe, okay? no matter what, right? Any reaction is going to cause chaos, cause entropy, right? Just think about it as you can see here, this athlete is a runner, okay? And he's transferring some of his energy, okay? He probably ate some sort of food or protein bar, carbohydrates, whatever, before he started running here. But he's turning all of that food into muscle movement, which is crazy, okay? Because what you're actually doing there is you're taking your molecules on the inside and you're reconverting them to get the potential energy out so that you can go ahead and move muscles and things like that. So you're turning like sugar into muscle movement, which is an energy conversion. And wait, energy can't be created or destroyed. So where did it go? Oh, look at him. He's sweating. He's hot. Heat. And heat is random molecular motion, and that's gone. That's gone into the atmosphere, right? So we increase the entropy of the universe just by doing these reactions, just by burning your food every single day. Okay. Yeah, the same thing. Look at a car engine. Man, you put in this beautiful, beautiful gasoline, and then you can see how, oh yeah, it turns into carbon dioxide and water, combustion reaction. But man, you ever put your hand on the hood of a car after it's been running for a while? It's very, very hot, right? It made the wheels go, got us to where we have to go. But boy, oh boy, we took one form of energy, potential, turned it into kinetic as the car was, the pistons are going and the car's driving down the highway. And yeah, we release some waste products, okay, which maybe somebody will be able to help make some order out of them later. But point is, no, on the most part, we lost heat. And down at the bottom, it's showing what you do. You are basically a car as well, right? You're a furnace, is what I like to say. So what you do is you eat your food, and then as long as you're breathing oxygen, this will be chapter 6 when we get there. But you're taking in this beautiful, look at that glucose molecule there. Oh, it's beautiful, right? C6H12O6. We love that guy. And all those little carbon-hydrogen bonds in there are what we're after. We're going to rip that apart, okay? And as long as you're breathing oxygen, boom, let's see here. You're going to enter your cells, okay, eventually your mitochondria, and you're actually going to shred that glucose to the point where, yeah, you get a little bit of usable energy as ATP, okay? But for the most part, that energy turns into heat. We're actually just these, I'm sitting in my basement right now, and there's a heater over across behind the wall over here. That heater is more efficient than I am at burning fuel. It's crazy, right? We over millions of years of evolution, this is what we're left with. We're furnaces, and if I was any more efficient, well, then my body temperature would be lower, and that wouldn't be good because my enzymes wouldn't work, right? So it's this delicate balance of taking in organic fuels. First law of thermodynamics is you can transfer them, okay, or transform them. I'm going to transform my sugar. I'm going to turn that into whatever, muscle movement, or talking to you guys right now. And well, what happened there? As I keep doing that, I'm getting ATP, right? But in a grand scheme, I'm losing energy overall to the universe. That's chaos. That's entropy. That's the second law. So, comprende. Describe the energy transfers when you climb to the top of a stairway. There you can see Rock, right? The man down in Philly. Yeah, you turn food, right? Potential energy into kinetic energy all the time. You climb the stairs. And not only that, you're climbing the stairs. So as you get to the top, hey, look at that. Yeah, now you have potential energy up there to go down the stairs, which is pretty crazy. So let's check out this video here. I don't know if it'll open up correctly. We'll try it out. All right. And we will allow.
Energy is the capacity to cause change. Kinetic energy is the energy associated with motion. Energy that is not kinetic is called potential energy, and is energy that matter possesses because of its location or structure. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy.
The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
Okay. So, makes perfect sense now, right? Now you get it. All right, let's see here. So, as we keep going here, chemical reactions either store or release energy. All right. You remember we were talking about like exerthermic probably before, or endothermic. That's just talking about the heat energy. This is talking about the total energy. As you go on, you'll learn about Gibbs free energy probably and total energy of a system and things like that. So basically, in endergonic reaction, you're talking about an input, right? A net input. That doesn't mean that it's all input. It just means overall there'll be an input of energy, okay? And that yields a higher energy product. So if you look here, you have photosynthesis is a good example. All right, starts with low energy reactants and CO2 and H2O. Okay, and it's kind of waste products. I know water's so important, but for us, we get rid of CO2 and H2O, and it produces sugars. Okay, so we started off with these low energy reactants, and we ended up with high energy products. How did that happen? Well, we're going to see sunlight and ATP and things like that. But you put that in, so, oh, that's why it's endergonic. Okay, there's a lot more potential energy in the products than there were in the reactants. Okay, and it did require energy for us to get there. So we definitely did some energy transformations. All right, well, you could probably guess what the opposite is then. Exergonic. So exergonic releases energy. Here the covalent bonds of the products have less energy. Okay, you've probably all done something like this before. For example, as you burn wood, you throw a log of wood into the fire, and what happens? The log just disappears. Well, we know matter also you can't create or destroy, right? So where did the log go? Where's the energy, right? Well, it turned into heat, right? Light. Those are forms of kinetic energy. That log had a lot of potential energy to it. So what did we do here? We started with high energy reactant in this case, okay, and we ended up with, oh yeah, ash is all that's left, right? We released a lot of that energy as heat and light. Okay, cellular respiration is a good example of this going on. Right? So what do? You take in glucose, or you take in whatever food and you break it down, and eventually you get some energy out of it. You started with a higher energy. Well, what happened to our energy? Heat, right? 98 point something degrees. They're talking about making that a little lower now. So 98.6 is generally what people say we should be, maybe a little cooler than that. And yeah, I'm 98.6, mainly because I ate food, right? I'm burning it down right now as I'm sitting here. So that's just an exergonic reaction all day long. I'm taking that food and I'm burning it down. Okay. And some energy is lost at heat, like I just said. And we want to make ATP. And then again, that'll be chapter 6. So cellular metabolism, when you hear that, a lot of people think metabolism is just how fast you break down your food. It's just talking about all your reactions, right? Your reactions that are going on inside your body. And finally, energy coupling. That's kind of an important thing to talk about here. energy coupling just means we're kind of talking about energy pathways here, okay? And all that really means is that when you take in energy, sure, that had to come from somewhere else. And now, why did I eat food? Why did I eat my mild flavored chicken wings, okay, tonight when I was watching an old Notre Dame game, because we're currently dealing with the coronavirus and there's no sports right now. So I was watching an old 1992, I think that's what it was. Yeah, November 14th, my birthday, 1992, Notre Dame versus Penn State. They called it the Snow Bowl. Notre Dame won on a 2-point conversion. That was huge. But point is, I was eating chicken wings. Why? Well, because later then, what can I do? I can go and use the energy that I did there for other processes, right? That's coupling, right? I'm going to release the energy of one reaction so I can put it into a different reaction, and I'll drive that reaction in. And that one will probably release some energy as well, and then you put it into another reaction. Okay, so there's a little firefly here. What's the whole point? What's he doing there? Well, he's trying to attract mates. Look at that, Luciferin going off there. He's a light bearer, right? He's go ahead and lighten up his butt there, hoping to find other mates. Okay, and he also has to, find more food, eat the food, digest the food, fly away from my daughters as they try and catch them, put them in jars, things like that. So, regardless, here we go. Cellular respiration is an exergonic process. Remember that energy must be conserved. What becomes of the energy extracted from food during cellular respiration? Well, again, chapter 6, cellular respiration, sure, we are going to get some as ATP. The whole point is, yeah, we want to get usable energy. We can't really run on food, but we can run on adenosine triphosphate. But we lose a ton. Like I said, my heater in my house is more efficient than I am as far as breaking down things and harnessing the energy from it. So we lose quite a lot as heat. Okay. All right. And finally, what is this guy? Talking ATP here. Okay. ATP shuttles chemical energy and drives cellular work. Ooh. Nearly everything uses ATP. Okay. We'll need to know this structure very well. And remember, we talked about Lynn Margulis and her endosymbiont hypothesis or theory now that yeah, maybe our mitochondria and chloroplasts are so complex that they used to be prokaryotes. Well, yeah, actually, what you're going to learn about next chapter is basically they create this gradient outside of their cells, and that's how it's a form of energy. It's a form of potential energy. What we do is we have this beautiful little organelle that makes most of our ATP for us, the mitochondrion. And what he mainly does is he takes components and he builds ATP for us, right? As long as we keep feeding the system, and again, it's going to be coupling. I'm going to be releasing and adding energy. And as you can see here, adenosine triphosphate. So adenosine, hey, look at this. I have a nitrogenous base, this case adenine. I have a 5-carbon sugar, ribose. And I have 3 phosphate groups. This is basically a nucleotide, right? So it just has some extra phosphate on here. This is a fully charged battery. So some books I've read talked about looking at these like compressed springs. That makes sense. It's kind of like the 3rd phosphate group right here. Think of this as like a spring. And if you remember, phosphorus is a weird atom here. Weird element. It doesn't obey the rule of octet very well. It's not very stable, these bonds here. And what's going to happen is this bond is like a spring that you push together and you compress it, and man, when you break that bond, it's going to shoot off that phosphate group. Okay, so there's a lot of potential to this molecule to do work for us. Now, how does that work? Well, the phosphate groups, like I said, they're negative, they're unstable, and when ATP is hydrolyzed, P group is released. Okay, you're left with something called ADP. So here we go. We have our ATP molecule over here. And you all, of course, remember dehydration versus hydrolysis. So we're going to hydrolyze the bond, right? We're going to break this P off. And when you do that, that P is now available. This is called ADP now, adenosine diphosphate. But this P is available to go and join somewhere else. Okay? And that's called phosphorylation. So when that P group transfers from ATP to another molecule, phosphorylation happens. And now that other molecule is probably energized, right? So whatever you're going to touch with that phosphate group is going to go do its own work. And what kind of work do we do? Well, you can see here, lots of different types. So 3 types of work here. It's more important to just think about what they are than the actual names. But chemical work, see what you're doing here? You're actually making reactants into products. So you're actually building something, okay, when you're talking about chemical work here. Mechanical work, sure, you're talking about like actual movement. Maybe you're running something along a microtubule from the Golgi, okay, to get to the membrane or something like that. Or maybe you're actually flexing one of your skeletal muscles, okay, going through a power stroke with actin and myosin or something like that, maybe. And then we also have transport work. And we talked a little bit about this earlier in the chapter. Sure, here's a solute particle, but look at this. I'm going from an area of low concentration to high. Oh, that's not easy. Boom, let's add some ATP. Let's phosphorylate this protein. And now we have the energy to fight that gradient and go against it and end up to where you're more concentrated, right? So ATP, very, very useful throughout your body and needed for cellular work. Okay, and of course this is just showing you that you can regenerate it. If you're talking about, you know, cells like muscle cells that use a lot, you can use up to 10 million ATP per second. Per second. So crazy. Energy from exergonic reactions comes in, right? And phosphorylation happens. So ADP and P was formed. Hey, we're going to eat food right now. Why are we eating food? Well, so we can phosphorylate our ADP, right? We can put the P back on there, but that took energy, right? So we had to couple it. We have energy coming into our system, and you'll learn how that happens soon. And now we got our ATP, and what was the whole point of doing ATP? Well, so we can break it down and put that energy into other reactions that need it, right? So it's all one big system, right? That's your metabolism. So comprende. Explain how ATP transfers energy from exergonic to endergonic processes in a cell. Well, again, exergonic processes hydrolyze the ATP, so you're ripping apart the ATP to form ADP, and then the ATP transfers its phosphate group, right? So that's becoming an endergonic process then. Wherever you phosphorylate, you're putting the energy in, and that's going to have this cascading effect of doing whatever that reaction had to do, right? Pretty cool, pretty cool. So that's pretty much it. I hope that was helpful for you guys. And if you have any questions, you can shoot me an email, and I will talk to you soon. Okay, thank you.